Look up at the night sky, and everything you can see, every star, every planet, every galaxy, makes up barely 15% of all the matter in the universe. The rest, it's completely invisible. We can't see it, we can't touch it, and light passes straight through it, as if it weren't there. Yet it outweighs everything visible by more than 5 to 1, and without it, galaxies would tear themselves apart. Scientists call it dark matter, and the race to detect it is one of the greatest detective stories in modern science. So how do you find something you fundamentally cannot see? Let's investigate. Welcome back to the channel, where we make the universe's deepest mysteries clear and exciting. Today we're following the evidence, from spinning galaxies to detectors buried over a mile underground. Stick around to the end, because the latest results have led scientists to an extraordinary new frontier they didn't expect. Let's get into it. Our story starts not with a particle, but with a problem. In the 1970s, the American astronomer Vera Rubin was studying how galaxies rotate. Based on the visible stars and gas, the outer regions of a galaxy should orbit much more slowly than the inner regions, just as the outer planets in our solar system orbit the sun more slowly than the inner ones. But that's not what she found. The outer edges of galaxies were spinning just as fast as the inner parts. By all the laws of gravity, they should have been flung off into space long ago. Something invisible had to be there, providing extra gravitational glue, a vast, unseen halo of mass surrounding each galaxy. This was one of the most powerful early signs that the universe is full of matter we cannot see. But spinning galaxies were only the beginning. The next clue came from the way the universe bends light itself. Einstein showed us that mass bends the path of light, like a lens. So by measuring how much the light from distant galaxies is warped as it travels past closer ones, astronomers can map out exactly how much mass is present, including the invisible kind. And again, there's far more gravity than the visible matter can account for. The most striking evidence of all comes from the bullet cluster, the wreckage of two galaxy clusters that smashed together. When researchers mapped it, they found something remarkable. The ordinary visible gas was clumped in the middle, slowed by the collision. But the bulk of the mass, revealed by gravitational lensing, had sailed straight through and sat off to the sides. The two had separated. That invisible mass, passing through the chaos almost untouched, behaves exactly as we'd expect dark matter to. It was as close to a smoking gun as astronomers had ever found. So we know it's out there. The next question is far harder. Can we actually catch a piece of it? To catch it, scientists have done something incredible. They've gone deep underground. This is the most direct approach. Wait for a dark matter particle to bump into ordinary matter and catch the tiny flash of light or charge it produces. The leading candidate particle is called a WIMP, a weakly interacting massive particle. The problem is that these interactions, if they happen at all, are unimaginably rare and faint. To stand any chance, detectors must be shielded from the constant rain of cosmic rays hitting Earth's surface. So they're built deep underground, over a mile down, beneath solid rock that blocks the interference. Inside, giant tanks of ultra-pure liquid xenon sit in total darkness, watched by hundreds of sensors waiting for a single telltale flicker. The most sensitive of these is the Lux Zeppelin, or LZ, experiment in South Dakota, a collaboration between the United States, the United Kingdom, Portugal, and South Korea. In late 2025, LZ released the results of the largest dataset ever collected by a dark matter detector, gathered over more than 400 days. And the result? No WIMPs, none. The same goes for its rivals, Sane Tent in Italy and Panda X in China. Now, that might sound like failure, but in science, it's anything but. Every time a detector looks and finds nothing, it rules out a huge range of possibilities, narrowing down what dark matter can and cannot be. It's like a detective eliminating suspects. The search box gets smaller, and the answer, whatever it is, gets closer. But here's the extraordinary twist I promised. These detectors have now become so unbelievably sensitive that they've started picking up something else entirely: neutrinos streaming out of the core of our own sun. In 2025, LZ detected these solar neutrinos with strong confidence, something once thought almost impossible. The catch is that this also marks a looming obstacle, nicknamed the neutrino fog, a faint background hum of neutrinos that will eventually become almost impossible to tell apart from a real dark matter signal. In other words, the hunters have become so good that they're now bumping into the very limits of what their technology can distinguish. It's a stunning milestone, even as the main prize stays out of reach. Underground detectors aren't the only weapon. Scientists hunt dark matter on three fronts. The first is indirect detection. Instead of catching the particles, telescopes in space search for the faint glow of radiation that should be produced when two dark matter particles collide and annihilate each other out in the cosmos. The second is production. At the Large Hadron Collider near Geneva, physicists smash particles together at near light speed, hoping to create dark matter in the lab. They can't see it directly, but they can spot the missing energy and momentum it carries away, like an invisible guest leaving footprints. And the third front is widening the net beyond WIMPs altogether. Many physicists are now hunting an entirely different candidate, an incredibly light particle called the axion, using detectors that work almost like finely tuned radios. With WIMPs proving elusive, these alternatives are gaining serious attention. So let's pull the threads together. We know, with very high confidence, that dark matter exists. The evidence from galaxy rotation, gravitational lensing, and the bullet cluster is overwhelming. We know it makes up the vast majority of matter in the universe. What we don't yet know is what it actually is. Despite decades of ever more sensitive experiments, no one has directly caught a single particle. Dark matter remains one of the biggest unsolved mysteries in all of physics, hiding in plain sight, holding the cosmos together. So, how do scientists detect dark matter? They follow its gravity. In spinning galaxies and bending starlight, they build the most sensitive instruments on Earth, buried deep underground, to wait for a whisper of contact. They scan the heavens for its echoes and try to forge it in colliders. So far, the particle itself has slipped through every net we've cast. But each nothing is a clue, each experiment sharper than the last. Somewhere out there, the answer is waiting, and the next great discovery in physics may be just one faint flash away. If this video shed a little light on the darkness, do me a quick favor. Hit that like button, because it genuinely helps the channel reach more curious minds like yours. Share it with a friend who loves a good cosmic mystery. And if you haven't already, tap subscribe and ring the bell so you never miss our next investigation into the unknown. Until then, keep looking up, because the universe is mostly invisible, and that's exactly what makes it so thrilling to explore.